Hello, my name is Roy Simpson. I'm a professor of mathematics at Summit College in Sacramento, California. This lecture in intermediate algebra is focused on solving systems of nonlinear equations, and I have titled this kind of differently than I normally title my lectures because I've actually written down that this is going to be part one of a lecture series on solving systems of nonlinear equations. Part two will be done later on, probably maybe a few weeks from now. And the reason why I'm doing this at this point is just to get an introduction to systems of nonlinear equations. So this will be a very brief introduction, but we've just gone through, if you're following my lectures in order, we've just gone through some problem-solving techniques in quadratic equations. We've done a lot of stuff with quadratics, including graphing and stuff like that. And so I just want to show you another little, not really application, but just another little thing that you can do with quadratics before we move on to bigger things. Now recall from previous lectures that a system of equations is just really a group of two or more equations that must be satisfied at the same time or simultaneously. What we've worked with in the past are systems of linear equations, so things like this right here. This is a system of linear equations because both equations have powers of 1 on their variables. That means they're linear. But in this lecture, we're going to focus on systems that are not linear. Maybe one of the equations might be a linear equation, but the other equation does not have to be. And we'll focus right now on quadratic systems. For our first example, we'll take a look at this system. Notice that the bottom equation here is actually linear. Both powers on both variables are 1, whereas the top equation is quadratic. So this is not a system of linear equations, it's a system of equations where one happens to be quadratic. And that's why we call this a non-linear system. To solve this, it really involves the same process that we would use to solve a system of equations. In general, what you're going to try to do is use a substitution method here. Often the elimination method, or Gaussian reduction, or Gaussian elimination, whatever your instructor calls it, is not really a good method once you get beyond solving systems of linear equations. So when you're doing nonlinear equations, substitution is best. However, I do want to reiterate, when you're working with linear systems of equations, then that is where you want to try to use the elimination method if you can. But in this case, we're going to go ahead and use substitution here. I happen to know that y is equal to 11 minus x, and at the same time I know that y is equal to x squared minus 4x plus 7. So if y is equal to both the top group of expressions and the bottom group of expressions, then I happen to know that these two must equal each other. It's like saying y is x and y is also z. Well, then you know that x has to equal z. That's just true, right? You know, that's gotta be true. It's also true by substitution. You could say, well, then if I know that y is equal to x, then I'm going to substitute that in for y in the other equation, and you'll get that x is equal to z. So that's what we're going to do here. Since we know that y is equal to 11 minus x, wherever I see a y in the top equation, I'll replace it with 11 minus x. So let's go ahead and do that. So this implies 11 minus x is equal to x squared minus 4x plus 7. At this point, I'm just going to isolate all the variables on one side. Because I have two different versions of my variable, I have an x squared version and an x version, a couple of them actually. That means that I'm going to have to use special techniques to solve this equation. And the special techniques require me to move all the variables to one side. So all variable terms I'm going to move to one side, and in fact I'll move all constants to one side as well. So I'll add, or I'll subtract 11 from both sides, and I'll also add x to both sides. I'm using the stacking method here to write my additions and subtractions underneath the proper terms. 11 minus 11, that's gone. Negative x plus x, that is gone. On the right hand side I get x squared minus 3x and then minus 4. And lo and behold, this is actually not too bad. Remember, when you get a quadratic equation, and this is quadratic because we have a power of 2 on one of our variables, the first tactic you should use for solving this is, well, to try to factor anything that they have common out of it. Well, there's nothing common to all three of these terms, so now the next step would be to try to factor this quadratic, which it does factor actually, to x minus 4 times x plus 1. Right? Two numbers that multiply to a negative 4 and add to a negative 3. And if two objects multiply to become 0, that means either the first object is 0 or the second object is 0. Now we can solve both of these. These are resulting linear equations. So I'll add 4 to both sides here and subtract 1 from both sides there, and you get these two solutions. X is equal to 4 or x is equal to negative 1. You should always check your solutions and check your answers to see if they work in the original equations. But in this case, in most of the cases that I do for online lectures, I usually don't check my answers. I know that's bad, but it's a great way to ensure that you are correct on an exam or something like that. The question is, what does this mean, that x is equal to 4 or x is equal to a negative 1? It means that we have two possible solutions. One is for x equals 4. We're going to go back to either of the original equations, either the first one or the second one, and trust me, the easier one is the second one. We can plug in x equals 4 to that to find out what y is. And 11 minus 4, we get that y is 7. So here's one solution, x equals 4, y equals 7. And now for x equals negative 1, again, plug that into either of the original equations to find out what the corresponding value of y is. Y is 11 minus that negative 1, that's 11 plus 1, or 12. So the solution for x equals negative 1 is y equals 12. Notice that we get two solutions to this system rather than the traditional one solution to the two systems. And this is because, well, this is not a linear system. Remember, when you solve a linear system, you have a couple lines, they cross at a single point. But in this case, these are not two lines. This is a line and a parabola. And I will show you very briefly here how you could see that you have two solutions by graphing both of these. Now, the first one I'll graph actually is this 11 minus x. It's actually an easier one to graph. When x is 0, y will equal 11. So what I'll do is I'll go up by 2's. 2, 4, 6, 8, 10, 12. So that's x equals 0, y equals 11. And then I'll do like, I'll plot a point for x equals 5 maybe. 1, 2, 3, 4, and 5. When x equals 5, y is equal to 6. Like this. And now you can connect those 2 points with a nice smooth line. Now we'll go ahead and graph the parabola here, and I'm going to use the techniques that we introduced in a previous lecture for graphing parabolas. I happen to know that all parabolas intersect the y-axis because they just get wider and wider and wider. So I will let x equal 0 and find out when that parabola intersects the y-axis. That happens at a height of 7. So let's see, that's 2, 4, 6, this is 7 right here. And now I'll ask myself, when am I at that height again? Because remember, a parabola is just a U-shape, so if I hit the y-axis here, I should be at that height again at some other x value. So I'll go ahead and let y equal 7. And as always with this method, when you try to solve this quadratic equation and you subtract 7 from both sides, all constants, or all constant terms, disappear. And now you can just factor the right-hand side, and you get this beautiful x times x minus 4 is equal to 0, which means that we have two objects multiplying to become 0. So either x is 0 or x is 4. And remember, this is answering the question, when is y 7? Well, y is 7 when x is 0 or x is 4. 1, 2, 3, 4. Height of 7 as well. Halfway in between those 2 points, in other words, at x equals 2, we'll have our axis of symmetry, which means the vertex is actually at x equals 2. And to find the y value for the vertex, we just plug x equals 2 into our quadratic equation. So that's y equals 2 being squared minus 4 times 2 plus 7. That's 4 minus 8, which is a negative 4, plus 7 is a positive 3. So I see my vertex is at 2, 3, which is right about here. And when you graph this out, you'll see that you get a parabola that intersects the line twice, here and here. Now remember, our solutions to this quadratic, or to this nonlinear system, were 4, 7 and negative 1, 12. 4, 7, which is actually that point right there, and negative 1, 12. Now, this is 2, 4, 6, 8, 10, 12. Wow, I almost did that perfectly. Freehanding that's pretty good. So that's pretty good. Negative 1, 12 is right there. So our picture does verify that situation. That's why nonlinear systems can have more than one solution. Let's try another example. In this case, I'm not going to graph. I'm just going to go ahead and solve. And we have choices here. Just as we would when we were solving systems of linear equations, we are going to go ahead and pick an equation and solve for a variable. And I'm looking at the bottom equation here, and I'm going to say I'd like to pick this equation and solve for x. So let me add y to both sides. I'll write that as negative 3 plus y. So I happen to know that x is negative 3 plus y, and I'm going to take that value of x and I'm going to substitute it into the other equation. Again, using the substitution method for solving systems of equations here. So that first equation becomes y squared is equal to 12, and then instead of times x, we'll write times negative 3 plus y. Now we'll solve this equation by distributing the 12. And I see that I have an equation that involves two different versions of y. One's a second powered version and one's a single powered version. That means I'm going to have to use a special technique to solve this equation. It's a quadratic equation, and if I have to use a special technique to solve a quadratic equation, that means I'm going to move everything to one side. So I'll go ahead and move everything over to the left-hand side. So I'm going to subtract 12y and add 36 to both sides. And every time I start with a quadratic equation, I ask myself, can I factor anything out that's common between these three terms? And there's nothing common between the three terms. So then I ask myself, okay, can I factor this? Two numbers that multiply to 36 and add to a negative 12? Definitely. That's y minus 6, y minus 6. Double check your work here. Negative 6 times negative 6 is 36. Negative 6 minus 6 is negative 12. This works out. So this tells me that, well, since I have two objects that multiply to become 0, that either the first object is 0 or the second object is 0. Which means essentially that y is just equal to 6. And remember, I have mentioned this a couple times in the past, But it's a good thing to remember. If you have a solution to a quadratic or to any actual equation where you have that solution occur more than once, we like to write down just a little bit of information about it, I guess. We like to say the multiplicity equals the number of times that solution occurs, 2. That solution occurred twice, so I'm going to say the multiplicity of that solution is 2. Again, we haven't used this yet, but the more that you get used to being able to say, oh, that solution is of multiplicity 2, 3, 5, whatever, the easier it will be once you start actually using that information in the future. So what's the big deal? Okay, now we have that y is equal to 6 is our solution, for y at least. But remember, we have an x variable in our original equation here. So what I'm going to do is plug this in for y into either of my equations, actually. I'll pick this bottom equation here. So x is equal to a negative 3 plus, instead of y, I'll write 6. So that's 3. So x is equal to 3. So when y is equal to 6, x is equal to 3. That is, these two equations, or the graphs of these equations, intersect only at one point, 3, 6. And the reason why they do that, I'm going to graph this out very quickly, is because, as you can see, and I'm not going to show you how I graph this because this is a special kind of graphing here, but the quadratic equation, y squared equals negative 12x, graphs as this parabola on its side, actually. And that's something we'll investigate later on in this lecture series. And then the line, well, that just graphs as a line, but notice they only intersect just barely at a point. Like, this line barely touches and then skips right off of the parabola. So they really only do meet at one point. And that's how sometimes you can get a solution to a or not a quadratic system, but a system of linear inequalities that only has one solution instead of 2. So let's try our hand at another system, a nonlinear system. This nonlinear system involves 2 quadratics, or in other words, 2 parabolas. Lots of possibilities for solutions here. But again, they're nice enough to give it to us where it's already solved for y. So we know that y is equal to 2x squared plus 3x plus 8. And at the same time, y is equal to 2x squared plus 4x plus 3. So I'm just going to use the substitution method by saying, well, wherever I see a y in that second equation, I'll just replace it with 2x squared plus 3x plus 8. Let's go ahead and do that. 2x squared plus 3x plus 8 is going to equal that 2x squared plus 4x plus 3. Now, I'm going to start moving things over, but here's one thing that you should recognize immediately. If I subtract 2x squared from both sides, you'll see that my equation reduces down from a quadratic equation to all of a sudden a nice, pretty linear equation. In other words, we have no x squared terms left over. So instead of moving everything to one side, I'm going to go ahead and isolate x variables. So I'll move every term that involves a variable to one side and every term that involves a constant only to the other side. So here I'll subtract 3x from both sides. Write that right there. Sometimes I take my time to show all these little steps. Might be boring too, sorry. And then I'll subtract 3 from both sides. And so in this case, we get a nice, beautiful 5 is equal to x. Beautiful little solution right there. And now I will go ahead and substitute in 5 for x in either of these equations. I will actually pick this second equation just because I can, I guess. So substituting in 5 for x, we get the following. 2 times 25, or in other words 50, plus 20 plus 3, that's 73. So our point of intersection occurs at 5, 73. Nice. And you could graph this out if you wanted to see that. And I recommend that you do that. Now, as a final example, I guess continue with the whole example sets here. We'll go ahead and solve another system of nonlinear equations, in other words, quadratic equations or higher powered equations. And again, they've given us this nice, beautiful y equals business. So I know that wherever I see a y in my second equation down here, I'll substitute in 2x squared, minus x plus 1. I'll go ahead and do that here. I should have funny stories as I do this, but I don't really have funny stories. Alright, so let's go ahead and move everything to one side. So I'll subtract x squared from both sides. I'll also add x to both sides, and I'll subtract 10 from both sides. I'll write that in here. Add x, subtract 10, and here we go. 2x squared minus an x squared, that gives me an x squared. A negative x plus x, they cancel, and 1 minus 10 is a negative 9. Everything on the right hand side should cancel out, and so I get this business. That's actually pretty easy to solve. If you only have one version of your variable, so it's quadratic, but I only have one version of that variable, I'm going to go ahead and solve, or in other words, isolate this variable. So I'll add 9 to both sides. I know I did all this work to get that 9 over there, but it just is a little bit better once you have one version of your variable to isolate the variable. And then I'll use the square root property to take the square root of both sides. Just recall that if you have x squared is equal to k, that implies that x is equal to plus or minus the square root of k. So in this case, x will equal plus or minus the square root of 9, which is 3. The reason why we have the plus or minus, recall, is that if x were positive 3, well, positive 3 squared definitely is 9, but x could have been a negative 3 because a negative 3 squared is also equal to 9. So we'd have to have both possibilities. This is very typical, by the way, of quadratic inequalities, or not inequalities, quadratic systems, in that we sometimes get two solutions. So let's write this down. We have x is equal to a negative 3, so I'm going to write for x is equal to negative 3. Now we'll find out what y is here by plugging this value of x into one of our equations. And I'm just going to plug it into this top equation. But you could plug it into the other equation, I suppose. It doesn't really matter. You get the same response. So let's see. This is 2 times 9, or 18, plus 3 plus 1. That's a 22. So in other words, when x is a negative 3, our output, or y value, is 22. And then we'll have another solution for x equals positive 3. Let me just plug that into the top equation as well. Let's see, that's 2 times 9, which is 18, minus 3 plus 1 is in minus 2, so that's a 16. So that means that when x is 3, our output, or our y value, is 16. So there are two solutions, negative 3 comma 22 and 3 comma 16. And since this is our last example, I'm going to go ahead and graph this really quickly, so again you can kind of see the graphing method that I like to use. Let's go ahead and graph this first quadratic. So maybe I'll write this for y equals 2x squared minus x plus 1. And I'm going to quickly go through my method of graphing so that I'm not going to write out every single step, just to show you how fast it can happen. I know it's a parabola, so I know it always has to hit a y-axis. So when x is 0, the y-intercept is 1. Let me go ahead and plot that on there. And now I want to know, because this is a U-shaped object and we hit the y-axis right there, I want to know when are we going to hit that height again. So I'm going to let y equal 1. I'm even being more verbose than I normally would be if I'm doing this by myself. So let's 1 equals 2x squared minus x plus 1. Subtract 1 from both sides. And then factor the right-hand side, as always. So this tells me my y value is equal to 1 when x is equal to 0, or when x is equal to a positive 1/2. I'll just plot that in there. Now halfway between those 2 points will be my axis of symmetry and my vertex. So I know the vertex will be at halfway between 0 and 1/2, which is 1/4. And I just plug that 1/4 into that equation to find my y value. And I'll go ahead and do that calculation very quickly. We find out that the y value for the vertex occurs at 7/8, which is just below the height of 1. So again, this is x equals 1/2, so this is x equals 1/4, and the y value is just below the height of 1. So it looks like a very shallow parabola here, but in reality it'll eventually start climbing nicely pretty far up. Okay, so that's one of our parabolas. Now let's go ahead and quickly graph the other one, and I will do this super fast now. I'll go into my normal fast mode here. And all I need is this little amount of space down here. For x squared minus x plus 10, I know the y value is at, or the y-intercept is at a height of 10, so it's 2, 4, 6, 8, 10. I know I'm at that height of 10 again, well, I'll just do it anyway, when y is equal to 10. Which implies that we have 0 is equal to x times x minus 1, or in other words, when we're at x equals 0 or x equals 1. So if that's x equals 1/2, this is probably x equals 1. So I know that I'm at the height of 10 again, right here. Halfway in between is my vertex. And plugging that x value of 1/2 into my equation, I get the following. Y equals 39/4, which is just shy of 10. So I'm going to go ahead and at x equals 1/2, shade that in right there. Connect the dots, and it looks something like this. So this is, by the way, because I'm graphing by hand, it's not going to be the best looking graph ever, but at least gives you the idea of, oh yeah, I do intersect at 2 different points. Now, graphing by hand means that you're never going to actually see perfectly which 2 points you intersect at, but it gives you the idea that you do intersect this parabola twice. All right, that's the end of this discussion on solving systems of nonlinears, at least the introduction to it. In a future lecture, we'll solve systems of nonlinears involving circles and cubics, stuff like that.